Okay, so this is a continuation of the series which I'm doing on differentiation, where I work through the E and EP questions in the EDEXCEL A-Level Maths book for Year 2. Okay, so this is exercise 9b, and the first question we have is question 4. Find the equation of the tangent to the curve y equals 2 to the power of x plus 2 to the power of minus x at the point 2 and 17/4. Okay, so as with any question about finding the tangent or the normal to the curve, let's first differentiate the curve and find the gradient at the point which they want us to find either the tangent or the normal. Okay, so we have a curve that looks something like this, and how would we differentiate this? Well, again, I'm not doing any teaching, but you should know that if you have something of the form a to the x, then the derivative of that is a to the x ln of a. And if you have something of the form a to the kx, then the derivative of that is a to the kx times k ln of a. And k is just some constant, so that should be fine. So then dy by dx of this, we see that this is of the form a to the x, so the derivative of this would be a to the x ln of a, where in our case a is 2. Okay, so we have that the derivative is 2 to the x ln 2, and this quantity takes the form a to the kx, where if you notice a is still 2, but k we have minus 1. So minus 1 times x, or in other words minus x. And so the derivative of this would be still a to the kx, so 2 to the minus x, times k, which is minus 1, times ln of 2. So all in all, this is minus 2 to the minus x ln 2. Okay? So this is our derivative of the curve. Now let's evaluate this derivative at the point 2. In other words, let's substitute in the point x equals 2 into the equation of the derivative, and let's see what we get as the gradient. So at x equals 2, our derivative becomes dy by dx equals 2 to the power of 2. So in fact, let me write that. 2 to the power of 2 ln 2 minus 2 to the power of minus 2 ln 2. Okay, so in other words, 2 squared is just 4, so we have 4 ln 2, and 2 to the power of minus 2 is 1 over 4. And you should know this from studying indices in year 1. Okay, and so this is pretty easy to evaluate. If you are confused by this, just think of this ln 2 as some constant. So you're used to, for example, solving something like this, 7a minus 3a, and this is 4a. Just think of ln of 2 as an a. It's a fixed quantity, it doesn't change. And so all we're doing is 4 minus 1 over 4, in other words 15 over 4 ln 2. Okay, so we found the gradient at the point 2, 17 over 4, and the gradient is 15 over 4 ln of 2. And they want us to find the equation of the tangent at the point P, let's call it 2, 17 over 4. So now we have all the tools we need to find the equation of the tangent, and this should be pretty simple. You've done this through GCSE and year 1. So it's y minus y1, in fact I'll write that out, y minus y1 equals m x minus x1. So x1 and y1 is the point at which you want to find the gradient, and m is the not the gradient, the point at which you want to find the tangent, and m is the gradient. So we have y minus y1, which is 17 over 4, equals m, which in our case is the gradient, 15 over 4 ln 2, x minus x1, again 2. So now this should be pretty simple to evaluate. So y minus 17 over 4 equals 15 over 4 ln of 2 times x minus 15 over 2 ln 2. Okay, and so the final answer is then y equals 15 over 4 ln 2 times x minus 15 over 2 ln of 2 plus 17 over 4. Okay, and this is the equation of the tangent to the curve at the point P, where the x coordinate is 2 and the y coordinate is 17 over 4. Okay, so the next question is question 5. where it says a curve has the equation y equals e to the power of 2x minus ln of x. Show that the equation of the tangent at the point with x coordinate 1 is this. Okay, so something like this, again, we have to find the equation of the tangent at some given point, and they haven't given us the full point, all they've given us is the x coordinate. So we have y equals e to the power of 2x minus ln of x, and let's call this point P again. We have P where the x coordinate is 1 and we don't have the y coordinate yet. It's pretty simple to find the y coordinate. All we have to do is substitute in this x value into here. So let's do that first. We have y equals e to the 2 times 1 minus ln of 1. In other words, we have y equals e squared minus ln of 1, which is 0, so e squared. So we found out that our y coordinate is e squared. Okay, so now again, because we want to find the equation of the tangent, a good first step would be to find the gradient of the curve at the point where x equals 1 and y equals e squared, like we've just found. So dy by dx is, okay, and the derivative of this, again, I'm not going to teach this, but if you have something of the form e to the kx, the derivative would just be k e to the kx, where you can replace k with any number. So for example, let's say if you have e to the 5x, then the derivative of that would be 5 e to the 5x. In our case, we have e to the 2x, so the derivative of this is 2 e to the 2x. Minus the derivative of ln of x, you should already know this, is 1 over x. Okay, so this is our derivative of the curve. Now, plugging in this x coordinate tells us the gradient of the curve at this point. So, let's plug in x equals 1. Our derivative becomes dy by dx equals 2e to the 2 times 1 minus 1 over 1. 1 over 1 obviously is just 1. So we have 2e squared minus 1. Okay, and now we have a gradient, so m equals 2e squared minus 1. We have a gradient of the curve at the point where the x coordinate is 1. And we know that the gradient of the tangent must be the same as the gradient of the curve at this point. Okay, so we have m equals 2e squared minus 1, and we have a point, let's call it P, 1 and e squared. So now we have everything we need to find the equation of the tangent. If they asked you to find the equation of the normal, you'd have to take the negative reciprocal of this gradient. Okay, so now again we have y minus y1 equals m x minus x1, and y1 is simply e squared. M is the gradient which we found here, 2e squared minus 1, x minus 1. Okay, so now we can expand the right hand side, so we have y minus e squared equals, so we have this entire quantity times x, 2e squared minus 1 times x, and then we have this entire quantity times minus 1. So we have minus 2e squared, and then minus 1 times minus 1 is plus 1. Okay, so let's rearrange this a little bit. Well, we need to show that the gradient, the tangent is this, and we're almost there. All we need to do is, it seemed like, add e squared to both sides. So we have y equals 2e squared minus 1 x, and if we add e squared to both sides, we get minus e squared plus 1, and I believe that's exactly what they wanted. Yeah, so this is the equation of the tangent to the curve at the point 1 e squared. Moving on to question 9. Prove that the derivative of a to the kx is a to the kx times k ln of a. You may assume that the derivative of e to the kx is k e to the kx. Okay, so this one can be a bit tricky, but once you understand the method, it's quite easy to understand. So we have y equals k, a to the power of kx. Okay, and we need to prove that dy by dx, the derivative is a to the kx times k ln of a. Okay, so the first step here is to kind of understand the trick, and once you understand the trick, these kind of questions become very, very simple. So the trick is that we are going to represent this quantity in a different form. Okay, so we're not actually changing what this is, All we're doing is we're representing it a bit differently. Okay, and how are we going to do that? Well, let's consider inverse functions. Okay, so you need to have some sort of basic understanding of inverse functions before you attempt this. So the two functions we're going to be considering are e to the x and ln of x. More specifically, we're going to be considering e to the ln of something. Okay, so for example, we know that e to the power of x and ln of x are inverse functions. Therefore, if you have e to the power of ln of, let's say, 3, this evaluates to just 3. Okay, because e to the x and ln of x are inverse functions, and therefore they cancel, and all you're left with is the argument inside here. And this works the other way around as well. So if you have ln of e to the power of, let's say, 72, this still works out to 72. Okay, and this doesn't have this not only works with constants, but it also works with functions. So if you have e to the ln of x cubed plus 3, this is simply x cubed plus 3, and vice versa. Okay, so whatever's inside the argument of the ln here is your answer, and whatever's the argument here is your answer here. Okay, so all we're going to do is we're going to put this inside our e and ln. Okay, so now that we know inverse functions, let's consider what we're going to do. So the trick is we place this entire thing inside an e, inside an ln. So we represent it like this. And we know that because e to the x and ln of x are inverse functions of each other, the answer is still a to the power of kx. All we've done is we've represented it a bit differently. Okay? And the reason we want to do this is we want to take advantage of this. We know that the derivative of e to the power of kx is k e to the power of kx. Okay? So once we've done this, we can use our ln rules. So we know that ln of, for example, a to the power of n is the same as n ln of a. So you can bring the power outside. Okay? And this works both ways, so you can even bring the power inside if you want to. But we're going to be using it going from left to right. So we want to be able to take the power outside. So what I mean by this is what I'm going to do is I'm going to take kx and I'm going to bring it outside. So I have kx e to the power of kx ln of a. Again, what we haven't done is change the value of this. This is still the same. All we've done is we've represented this differently. Okay? And that was the trick. And now we can evaluate the derivative. Okay? So we have y equals e to the kx ln of a. Okay? And now we can make use of this. So we know that the derivative of e to the kx is k e to the kx. So k is some constant. And what we need to do is identify the constant in our case. So x is the function, but k and ln of a is the constant. So it's a bit confusing here. They've used a k and we need to use a k as well. But once you identify that k and ln of a is the constant, we can see that the derivative of this would be k ln of a times e to the kx ln of a. Okay, this is like saying, for example, let's say e to the... Okay, so let me work backwards first. So you know that e to the 3x differentiates to give 3 e to the 3x, right? Because 3 is a constant. Okay, and we're differentiating with respect to x. So now if you have e to the 3x ln of 2, the constant is 3 ln 2. So the entire constant comes down, right? So the derivative of this would be 3 ln 2 e to the 3x ln of 2. Okay, I hope that's clear. So we've brought down the entire constant and we've left the x by itself. Okay, so once we've done this, we've almost finished the question. So we have k ln of a times, and this quantity, remember, is just a special way of showing this, because we haven't actually changed the value. So we have times a to the power of kx, and so we have that dy by dx is a to the power of kx times k ln of a, okay, as required. Okay, so the next question is question 10. F of x equals e to the power of 2x minus ln of x squared plus 4, where x is greater than 0. Find f dash of x. Okay, so this should be pretty simple. If f of x is this quantity here, you currently don't know how to differentiate ln of x squared. You will see this using the chain rule later on. But for our example, we can manipulate this a little bit. So, like I mentioned in the previous question, your log rules state that if you have ln of x to the power of n, what you can do is you can bring out the power. So we have n times ln of x, and this works both ways. Okay, so if you have n times ln of x, you can bring in the power. But in our case, it's more useful to bring out the power, so let's do that. E to the power of 2x, so what I'm doing is I'm bringing out the 2. So we have ln of x squared, and what I'm going to do is I'm going to bring the 2 out. So I have 2 ln of x. Okay, so minus 2 ln of x plus 4. Okay, and so again, I haven't actually changed the value of the function, but all I've done is manipulate it a little bit. And now I can go about finding the derivative. So I know that the derivative of e to the power of kx is just k e to the kx. In our case, k is 2. So I have 2 e to the 2x minus 2 times the derivative of ln of x, which is 2 times 1 over x. Remember, constants don't change the value of the derivative, okay, because you're differentiating with respect to x. And then the 4 vanishes. So you have 2 e to the 2x minus 2 over x. And this is your derivative, f dash of x. Okay, so 10b. The curve with the equation y equals f of x has a gradient of 2 at the point P. The x-coordinate of P is a. Okay, so we know that P has x-coordinate a, and we don't need the y-coordinate in this case. We know that the gradient m is 2. In other words, f dash of x is 2. Okay, at the point where x equals a. So we know that f dash of a must equal 2. And so let's plug in the information we know. We know that 2 equals, and instead of x we need to plug in a because that's the x-coordinate of this point. So we have 2 e to the 2a minus 2 over a. Okay, multiplying everything by a, I get 2a equals 2a e to the 2a minus 2. So I'm going to add 2 to both sides, and I'm going to take away 2a. So what I get is 2 equals 2a e to the 2a minus 2a. Dividing the entire equation by 2, I get 1 equals a e to the 2a minus a. And I can factorize out an a on this side, so I have 1 equals a e to the 2a minus 1. That's what they wanted. Okay, so moving on. A curve C has equation y equals 5 sine 3x plus 2 cos 3x, and x is between minus pi and pi. Show that the point P02 lies on C. Okay, so this is a 1-mark question, so it shouldn't be too difficult. We just need to check that once we plug in x equals 0 and y equals 2, that this matches up. So, does 2 equal to 5 times sine of 3 times 0 plus 2 times cos of 3 times 0? Okay, so this gives us 5 sine of 3 times 0, which is 0, plus 2 cos of 3 times 0, which is, again, 0. So we know that sine of 0 is 0 and cos of 0 is 1. So we have left-hand side, which is 2, is equal to 2 times 1, which is 2. And that matches up. So that was A. Part B is find an equation of the normal to the curve C at P. Okay. Again, when we're finding tangents and normals, let's first find the gradient at the point at which they want us to find the tangent of the normal. So we have P02. So dy by dx would be 15 cos 3x minus 6 sine 3x. Again, these are just standard functions which you should be able to differentiate already. Okay, so dy by dx is this, and we need to plug in x equals 0. So at x equals 0, we have dy by dx equals 15 times cos of 3 times 0, which is 0, minus 6 times sine of 3 times 0, which is 0. So this is 0. We know that cos of 0 is 1. So our derivative is 15 at this point. So if we were to find the equation of the tangent, then we'd simply use this m equals 15. But we need to find the equation of the normal. So we must take the negative reciprocal of this. So we know that our m is minus 1 over 15. And we know our point P is 0, 2. Okay, let me just double check it's 0, 2. Yeah. And now we can easily find the equation of the normal. So we have y minus y1 equals m x minus x1. So we have y minus y1, which is 2, equals m, which is minus 1 over 15, x minus 0. Okay, so then our equation just becomes y minus 2 equals minus 1 over 15 x, and then y equals minus 1 over 15 x plus 2. And if they specify what form they want the equation of the line in, then you must give it in that form, but otherwise this is fine. Okay, this is the last question in exercise 9b, which is of the form EP. Okay, so this is question 12. The point P lies on the curve with equation y equals 2 times 3 to the power of 4x. The x-coordinate of P is 1. They haven't given us the y-coordinate. Find an equation of the normal to the curve at the point P in the form y equals ax plus b, where a and b are constants to be found in the exact form. Okay, so again, they want the normal. So first, since they haven't given us a y, let's find that out. So we find the y-coordinate by plugging in the given x-coordinate. In our case, the given x-coordinate is 1. So y equals, and we plug it into the equation of the curve. So y equals 2 times 3 to the power of 4 times 1. In other words, that's 2 times 3 to the power of 4, which is 162. So now that we found the point, we found the entire point. So if I make some space here. Now, again, when we need to find the equation of a line, so an equation of a tangent or a normal, we need a gradient and we need a point. So we've already found the point and we need the gradient at this point. So let's do that. How do we find the gradient of a curve at a certain point? Well, first we need to differentiate. So we have dy by dx equals 2 times the derivative d by dx of 3 to the power of 4x. Okay, and all I've done here is I've taken out the 2, because if you think about it, we're differentiating with respect to x. So anything with the x I can differentiate, anything not including an x I can just multiply in at the end, because constants actually don't change the value of a derivative. Okay, so then I have 2 times the derivative of this, 3 to the power of 4x, you should know is 4 ln of 3 times 3 to the power of 4. Okay, and so our final derivative is 8 ln 3 times 3 to the power of 4. Okay, and so once we found the derivative, let's find the gradient, and we find the gradient by plugging in this x-coordinate. So if we plug in this x-coordinate, we get the gradient of this curve at this point. So at x equals 1, we have dy by dx equals 8 ln 3 times 3 to the power of, so this should be an x here, my bad, times, so times 3 to the power of 4 times 1. Okay, in other words, 3 to the power of 4. And this evaluates to 648 ln 3. So this is the gradient of this curve, y equals 2 to the power of y equals 2 times 3 to the power of 4x at this point P. Okay, and once we found the gradient, we're almost done. So the key thing here is that they want us to find the equation of the normal. Okay, so we need to take the negative reciprocal of this. If they wanted us to find the equation of the tangent, then we could take this gradient as it is. But since it's the normal they want us to find, we take the negative reciprocal. So minus 1 over 648 ln of 3. And we're already given a point 1, 1, 6, 2. Now we have the two things which we need to find the equation of a line. Okay, so y minus y1 equals m x minus x1. So we have y minus y1, which in our case is 162, equals m, which is minus 1 over 648 ln of 3, x minus 1. Okay, and now we just need to rearrange this a little bit. I'm pretty sure you could probably leave it in this form. Actually, no, you couldn't, because they've specified what form they want it in. Ax plus b. So y minus 162 equals, let's expand the right hand side, so we have minus 1 over 648 ln 3 x minus 1 over 648 ln 3 times minus 1, so we get plus 1 over 648 ln 3. And then so our final answer is y equals minus 1 over 648 ln 3 x plus 1 over 648 ln 3 plus 162.